Bang. Okay. And here's our presentation. Okay, can you see this, Bruce?
Yep.
Great. So what we're going to do today is build on what we saw last time with forms and archetypes. We're going to really focus in on what Michael Levin has been doing to advance biology. And when I talk about these forms, that's why I call it metabiology, because it's really above what current day biologists are studying. They're all hung up in the chemistry and the folding of the proteins, and it's a very bottom-up, very hardware-oriented approach. And his approach is much more software-oriented. And the forms that we're talking about are the forms for your body, for your fingers, your feet, your head, your arms, your legs, the organs in your body, your lungs, your heart, your kidneys, your liver, your lymphatic system, all of these things, they all have forms. And what Levin is arguing is that if we can, we already have this stuff built into us. These are the forms of healthy organs. And if we can activate those forms, then they'll just naturally get rid of disease. It'll just
Oh, I see.
disappear. You'll resonate with the right form. The reason why you're sick is you're resonating with some flawed version of that form. That's why your kidney isn't working, or you have heart issues,
Ah,
whatever it is. So
right.
that's the hypothesis. And is it true? Well, we'll see. We're not there today, but there's a lot of indications that it's going in the right direction. So that's why we're going to focus on forms. And let's going to go right back to the beginning here when we talked about having a basic idea. It's a form or a pattern or an archetype, and they're everywhere, so they resonate with other similar entities, and that's what gives it its power, is that you can resonate with these other things. So that's how the healing would take place, is whatever uh, medical technology you have would generate the correct form, and your organ would get healed. It would resonate there with what's in this medical device. And what this is where Ron Cowan comes in, because what he saw was these forms are probably in this information that coats the ether compartments of space, of everything around us. They
Right.
control all the forces, and so they're a natural place where the forms would reside. But we don't know. We're just talking about that. So uh, the phrase we'll use as above, so below. These forms are useful at different levels in the microcosm, at the level of chemistry, biology, and even consciousness and unconscious thoughts and activities. This is where Carl Jung was very active, with archetypes being a type of form that was involved with your conscious and unconscious activity. So this is really fundamental. Where in the world, uh, it's just not mainstream biology right now is what the problem is. So uh, this is what Ron said. The key thing is these information blocks are constantly scanning everywhere, and this is probably what Jung called the collective unconsciousness that's everywhere throughout the universe. So what we saw here, we have three complex spatial dimensions uh, for matter and dark matter. Then we have these six compactified dimensions, but three are for matter, three are for dark matter, and they're very small. They're like 10 to the minus 30th meters in size, wrapped around any line that we could draw. So it's hard to appreciate what 10 to the minus 30 meters is. So if we look at the speed of light, which is 3 times 10 to the eighth meters per second, then we're seeing, if we just get rid of the meters, just divide wavelength into meters per second, we have 3 times 10 to the 38th, or 300 gigahertz, which is a lot of hertz, a lot of vibrations there. So and this ignores the real higher realms where there's 3 compactified spatial dimensions that connect the 3 for matter and the 3 for dark matter. So these things are really running at very high levels, and this is probably what it means when you hear people say you have to raise your vibrations as you're getting up into these compactified realms to resonate with these things. uh, Ron talked about how he was probably a spiritual or an etheric entity who was on the planet of another star, and some sort of nova occurred, and he drifted through space and landed on Earth. So when he landed on Earth, uh, he was just quiescent up to that point, but Earth was nice and warm, and so the heat woke him up. And unfortunately, when he landed here, it was so early, there was nothing but single cell life, what we call today bacteria and archaea. Archaea is the stuff you find in your gut. And it's collectively, it's called prokaryotic life. So he was clearly involved in trying to make it be multicellular eukaryotic organisms. And this led to the world that we see around us today, where the cells specialize in function. The single cells don't have any specialization. They just do their thing. So what happened here? Well, if we go back and look at when Ron and other people were running around, we can see 4 basic legends occurring. Who knows if they're true? The first one was of a realm called Hyperborea, and this was a paradise that was populated by probably etheric spirits. So these are not things of matter. They're there on Earth, and they were having a fine time uh, and living quite long. But then they seem to disappear. We have no idea what happened. And then after them came Lemuria or Mu, and this was populated by life forms that were partly material and partly etheric, apparently. And they spent a lot of time meditating and were very much linked to one another collectively. And then they disappeared. And then the next one we found was Atlantis, which itself went through a number of restarts before it reached a very high point where it was using resonance and so forth, as we'll see, uh, to generate energy, probably for more than 1,000 years. And then it fell. And just as an aside, there's a special place for the Indian subcontinent. And this is found in this poem we touched on, the Mahabharata. And no one knows if this is real. It's an epic poem. It's 10 times longer than the Odyssey and the Iliad put together, but it combines myth and philosophy and all kinds of things. And the central story is a war that takes place that no one knows if it really took place. They think it might have taken place 1,000 BC, but this is just a guess. But we do have some recent archaeological evidence. They found a submerged city in the Indian Ocean, just close to the Arabian Sea, called Dwarka. And this is an evidence that there really was something to do with the Mahabharata and so forth. But it's underwater now. And this is where Krishna lived, apparently. But when they dated everything, it's 9,500 years old. So it seems to match what's in the Mahabharata, but it's much older than the pyramids, for example. And so it goes. So India has its own special place. I know that I read some Vedic transcriptions of Vedic manuscripts, and they had in them how to run a Vimana. So a Vimana is a flying car, and they had some sort of motor in it that involved mercury, and it would circulate the mercury uh, rotate it at high speeds. And then the directions were all, just, put the key in here, step on the control pedal to lift off and so forth. Just, when you have a car, you don't really know how the engine works. There's nothing there that really says this is what's really going on. So this was just an owner's manual for one of these Vimanas, and it made you wonder what in the world were they doing? Just as a different example, we have the Hopi here, who said there were these different ages. First, the age of fish, of things in the oceans, then ants, then reptiles, birds, and mammals today. And so Atlantis would play into the mammal side of things. But the key thing about Atlantis, the reason why we're keen on this, was their crystals. And the crystals were used to create energy, to heal people, to allow them to fly, to travel anywhere on Earth, and so forth. And these forms lived in a space of forms. So it's called the metaspace because it's above the space that we all see. We can't see the space of forms. And what happened was Atlantis saw it was going to sink, and so it sent out colonies to preserve these ideas. They were scattered around the earth. Pythagoras left Greece around 600 BC, and he went to Egypt to learn about this. And then he returned to Greece and he shared some of this knowledge with Plato. And Plato wrote this up as a theory of forms. So what he's saying is that the ultimate reality is a world of perfect, timeless, and unchanging abstract concepts called forms or ideas. So all of this apparently came from Atlantis, of which the physical world is imperfect and a changing imitation of what's truly there. So we all agree that the world that we see is not the true reality. So it's interesting how this idea carries over with Plato and his theory of forms. So the perfect and eternal form of a chair is going to exist independently of any physical chair, which is merely a flawed copy, or a form of a kidney or a heart is independent of any physical heart or kidney, which is, again, a copy. So the true knowledge, according to Plato, isn't gained through the senses of the physical world, but through especially meditation and contemplation of these forms through the soul. So, very Eastern in its views. And the world of forms, again, is a non-physical spiritual realm that contains these forms, these unchanging essence, and they're used again and again, and wherever they go, they resonate with other similar forms. So this is the realm of true reality and knowledge, and the information that goes everywhere, that links everything, makes all this possible. And we have the world of appearances, which is the world that we perceive through our senses, and this is not really the ultimate reality. So the forms really are these archetypes that Jung described. So each concept has a corresponding form for its perfect blueprint or ideal model. So that includes concrete things like trees or chairs, as well as abstract qualities like beauty or justice. And there's all kinds of copies and imitations, but the physical world is a mere imperfect copy of the corresponding form in the ideal realm. And so the senses only provide information about the physical world, which can never really lead to true certain knowledge. This you can only get by grasping the eternal and unchanging forms through deep meditation. So Plato believed that the soul is eternal, and the soul came from the world of forms. The soul is what is quite aware of what these forms are. And so before being incarnated into a physical body, the soul was directly in contact with the forms. And the process of learning in this life, according to Plato, is a process of recollection or remembering the forms that the soul already knows before it incarnated. So the soul is again a piece of this collective unconscious that's everywhere in the universe, and the consciousness has free will and makes choices through life, which the soul records in this Akashic record. So the forms are expounded upon in Plato's dialogues and general speech, in that every object or quality in reality, dogs, human beings, mountains, colors, courage, love, goodness, has a form, and a form answers the question, what is that? Plato was going a step further, though, and he asked what the form itself is. And he supposed that the form essentially uh, was really the true form. The phenomena that we see are merely shadows mimicking the true form, and that's the problem. The problem of universals. How can one thing in general be many things in particular? Was solved by presuming that a form was a distinct or singular thing, but caused plural representations of itself in particular objects. So many of these forms are used again and again at different levels of the reality that we see around us. Now, these forms are really the essence. If you don't have the form, then there wouldn't be anything there. For example, you wouldn't have fingers or toes or a heart, the examples like this. So the form is really the essence of everything. And Plato had a student, Socrates, who held that the world of the forms is transcendent to our own world, which is the world of substances. And this world of forms is the essential basis of reality. So forms are the most pure of all things, and Socrates believed that true knowledge and intelligence is the ability to grasp the world of forms with one's mind. Plato believed that long before our bodies ever existed, our souls existed and inhabited heaven. So Ron would probably be an example of this, because he apparently was etheric and then incarnated. Uh, when they became directly acquainted with the forms themselves, uh, then they started to really understand true knowledge through what the forms are. But the problem with the forms is you learn so much more through sensory experience, because the forms aren't in the physical world, where they're corrupted in some sense. They're not perfect. So our real knowledge of the form must be a memory of our initial acquaintance with the forms in heaven. And we seem to learn, in fact, by just remembering. One example that comes up for this is language, is that apparently uh, people, by just listening as kids, when they're growing up, they can learn a language. And in particular, the grammar for the languages is all different, yet we seem to have some form that's a part of our consciousness that allows us to, after a period of time, speak a language. And this is just taken for granted, but it's something that's right in front of us, and it's probably an instance of a particular form here, a mental form that allows you to learn a language. So we now get to where Michael Levin is. He's building on all this. Everything we talked about is easily before 0 AD. So here we are 2,000 plus years later, and he said, okay, for over 100 years now, biologists have been working to understand biology at the level of chemistry, uniting biology with chemistry. And this was a great triumph that happened with physics and chemistry. There was a periodic table of elements, and this led to the development of a Bohr model of the atom, and then quantum mechanics. And in turn, this led to the unification of chemistry with physics. This is inorganic chemistry, not organic chemistry. And so, since this works so well, uniting chemistry and physics, why not try and unite biology and chemistry? And so here we have to deal with genes, but we have to deal with chemistry And here the chemistry is incredibly complicated, to put it mildly. So the gene linked phenotype to the molecules of chemistry and then a more abstract and promising world of information. The gene itself is probably a form of some sort that is the basic building block in biology. Now, there have been a lot of successes with this that have led to new understandings. There's always money available for trying to treat cancer through some sort of gene therapy or sickle cell disease. But the reality is there's been many more failures than successes. And a lot of the successes, uh, you know, we look at the disclaimers on the TV ads for these drugs, and the list of things that can go wrong is huge. And this is supposedly is a good drug that made it through the testing process. So you can imagine what didn't make it through that's there. So another thing that you hear a lot about is DNA sequencing, that we can now go ahead and take some DNA and actually sequence it for probably less than $100 in a short period of time, say an hour or so. You'd be able to have a complete sequencing of someone's DNA. The problem is now what do you do with it? What good is that? But these are the successes. So people like Michael Levin are taking a new approach, and he's, as we said, at the Tufts University, and he has ties to Harvard, and he has about 40 to 50 graduate students here, probably 3 different buildings at Tufts. He's got a whole program here that he's orchestrating and doing this stuff, and he's giving lots of talks on what he's doing. So he's really focused on the innate intelligence of the tissues and organs, and he really argues that networks of cells, the way that they perform is they're driving towards some goal, and they achieve their goal by using bioelectricity, which is everywhere. Every cell in your body has a electrical potential from the inside of the cell to the outside of the cell, typically 10, 20, 30 millivolts. So there's no lack of electricity. So this is what allows you to get to these goals, so the cell can do the things that it has to do. And he uses terms like goal and not intelligence, because people in the field say, well, uh, this is not the way things work. And he says, well, I think it is the way things work, so I'm going to have to define these ideas. So he goes in and he reprograms the goals of a group of cells, and he lets them do the work of reversing disease and so forth. And you'll see examples of this in some of these videos. So let's go to the first video here. I'm going to get out of this and go here to the first video. Here it is. Give me a second. We're only going to do part of these, but it'll give you some flavor. He has many, many videos. Okay, can you see this, Bruce?
Yep.
Okay.
I'm very excited for this. Take it away.
All right. Thank you so much for that extremely kind introduction, and thank you for having me here to share some thoughts with you. You can find all of the peer-reviewed stuff, the papers, the data sets, everything is at this address. And then here is a personal blog of what I think some of these things mean. What I'm going to talk to you about today is bioelectricity, but specifically the use of bioelectricity as an interface to the plasticity of the agential material that makes up your body. And I think this has massive implications for biomedicine going forward. I like to think of the end game of our field as something called the anatomical compiler. Just think, someday you should be able to sit in front of a computer and draw the anatomy of the animal, plant, organ, biobot, whatever it is. You should be able to draw it, And this system will then compile that specification into a set of stimuli that would have to be given to cells to get them to build exactly what you want. Now, so in this case, I'm showing you this three-headed flatworm. But if we had something like this, then birth defects, traumatic injury, cancer, aging, degenerative disease, all of these things would go away. If you could convince cells to build whatever you wanted them to build, all of these things would go away. Now, why don't we have something like this? We're actually very far away from it. Where we stand today with molecular medicine is that we're very good at this kind of information: which cells and what the cells are doing, what individual proteins are binding to what other proteins, which genes turn on and off other genes. The molecular information is very strong, but we're quite a distance away from being able to restore limbs and repair birth defects and things like this. And so why is that? I'm going to argue that this is because where medicine is today.
With the SwiftReader X, you can make your everyday easier. Your deliveries can be
is where computer science was in the 40s and 50s. In those days, in order to reprogram a computer to get it to do something different, you would have to physically interact with the hardware. Here she is. She's rewiring the machine to get it to do something different. And so what I think we've just now started scratching the surface of is to understand actually the plasticity and more specifically the intelligence of the living material, meaning that it is reprogrammable. And for the same reason that you would laugh if I told you today that on your laptop to switch from Microsoft Word to PowerPoint, you'd have to get out your soldering iron and start rewiring the thing, right? It's we don't do that anymore. Why? Because we understand that the material that we're dealing with is reprogrammable, and living material is that and more. So this is what we are made of. We're made of individual cells. So here's this is a free living organism called the Lacrimaria, but it gives you an idea of what individual cells can do. This thing is incredibly competent in its own little sphere of influence here. There's no brain, there's no nervous system. It handles all of its physiological, metabolic, and so on, and needs all in one cell. And in fact, all of us were a single cell once. And these cells did this amazing process of embryonic development where they became one of these complex organisms, or even perhaps a human. And in fact, even below the single cell level, the molecular pathways within single cells already have learning capacity, right? The different signaling pathways and gene regulatory network components come together into a collective intelligence that is able to form 6 different kinds of memories, including Pavlovian conditioning. You don't need a brain, you don't need neurons, you don't even need the cell. It's just the molecular pathway alone has this capacity, and we are now creating devices that we're using to train these pathways, and then there's many applications like drug conditioning and so on. So the idea here is that bodies are made of multiple levels, not just of different scales of organization, not just the nested dolls structurally, but actually every level has its own capability of solving problems in different spaces. So we're familiar with animals solving problems in the behavioral space, but your molecular networks, your cells, your tissues, all of them are constantly navigating these other problems. And we are made of this amazing multi-scale competency architecture. I'm going to give you just one example because time is short. I'm going to give you just one example of the kind of problem solving I mean. So this is a tadpole of the frog Xenopus laevis. You've got the brain here. Here's some nostrils. Here's the mouth. These are the eyes, and this is the gut. And so these tadpoles have to become frogs. In order for a tadpole to become a frog, it has to rearrange its face. So the eyes have to move, the mouth has to move, the nostrils, everything has to change. And you might think that this is a hardwired process, that somehow the genetics specifies that every organ moves in the correct distance, the correct direction, and then you get your frog. Well, we decided to test this because anytime you're going to make a claim about the level of intelligence of something, you have to do experiments. You cannot just assume. So we decided to test it. We made so-called Picasso tadpoles where everything is scrambled. So the eyes on top of the head, the mouth is off to the side here. Everything is mixed up, like a kind of like a Mr. Potato Head doll. Everything is mixed up. And then what we found is something amazing, that these animals give rise to pretty normal frogs.
Hi, Kurt here. If you're enjoying this conversation, please take a second to like and to share this video with someone who may appreciate it. It actually makes a difference in getting these ideas out there. Subscribe, of course. Thank you.
And what we found is something amazing, that these animals give rise to pretty normal frogs. And that's because these organs don't just move the right distance in the right direction, because then they would be wrong. They actually move in whatever way is needed through novel paths to get to where they're going, and they make a correct frog face. So this ability to reach your goal from different starting positions, right? Get your goal satisfied despite novelty, things that you did not know were going to happen, is a key aspect of intelligence, of intelligent behavior. And so now you have to ask a simple question. How do these cells and tissues know what a correct frog face looks like? Okay, how do they store the memory of the endpoint? And we know they can remember the endpoint because they stop when they get there. When they achieve the normal frog face, then they stop. So how do we actually, how can we think about a collection of tissues storing these kinds of memories? Well, we took our inspiration from what happens in the brain, which is a sort of familiar system where groups of cells store memories and guide behavior, in this case in three-dimensional space. And the way it works in the brain is this. You have a network of cells. So here's a neuron. It's touching this other neuron down here. It has these little proteins called ion channels, which let charged molecules in and out. And as a result, it acquires a voltage. And that voltage may or may not be propagated to its neighbors. And the flow of electrical signaling through this network is what underlies all cognitive activity. And so here is a video that this group took of a zebrafish, a living zebrafish brain. And you can see this amazing electrophysiology going on here. And it's the commitment of neuroscience that if we could decode this, so this is the project of neural decoding, if we could decode this, then we would be able to read out the memories, the goals, the preferences of this animal. And so that is what we would like to do, but outside the brain. We want to do it for the rest of the body. And the reason that's possible is because actually this amazing system of using bioelectricity to integrate information, store memories, and guide intelligent behavior is way older than brains. It, in fact, evolved around the time of bacterial biofilms. It's extremely ancient. And in fact, every cell in your body has these ion channels. Most cells have these electrical synapses to their neighbors.
Your body language speaks louder than your resume. As behavior
and your tissues are running these electrophysiological networks. And so you might ask the question, what do they think about? We know what our brain thinks about. What do the body tissues think about? And so I'm going to tell you that one thing they think about is shape. They think about arranging the body in the correct shape and then maintaining that against aging, against injury, and against cancer. And we can start. So here, much like this video of this brain, we can start taking a look at the bioelectrical signals. This is a frog embryo. What you're seeing is a time lapse of a frog embryo, and you can see all the conversations, the electrical conversations that these cells are having with each other. Could we decode this? And here's what some of these patterns look like. First of all, this is something we call the electric face. So again, here's a time lapse of a frog embryo putting its face together. And there's a lot going on here, but if you look at one frame of that video, you can see that prior to the appearance of the craniofacial organs, this is the map that it's going to build. Here's where the animal's right eye is going to go. Here's where the mouth is. Here are the placodes. So this, we are literally, what you are seeing here is literally reading out the electrical memories that tell the cells what a correct face is supposed to look like. And this is what guides normal development. So we can now begin to read out what it is that these cells remember as the correct thing to build. And not only does this bioelectricity serve as a kind of cognitive glue that binds individual cells into a global vision of what the whole large-scale thing is supposed to look like, it actually does this for multiple embryos. Here, you can see if we poke this embryo, all of these guys find out about it. Okay, see this? So this injury wave. So this bioelectrical communication tends to merge subunits into a coherent whole. And you can see here, these are individual cells. By the way that we are monitoring all of this is with voltage-sensitive fluorescent dyes. That's a technology that we developed to use these dyes to help understand what the cellular collectives are thinking. Now, watching these patterns is all well and good, and in fact, you can use them to diagnose birth defects and so on. But of course, the more important thing is to start to rewrite these pattern memories. So if I'm telling you that these are memories, on the one hand, you want to be able to read and interpret them, and on the other hand, you want to be able to reset them for therapeutics. And in order to reset them, we don't use electrodes or fields or magnets. There are no waves, no frequencies, nothing like that. What we're doing is manipulating the natural interface that these cells are using to control each other. So on their surface, they have these ion channels which set the voltage, and then here they communicate that voltage to each other. So just like neuroscientists do, we take all of those tools and we can use pharmacology to turn the channels on and off. We can use optogenetics and so on. And so we can control the voltage and the communication between cells. So I'm going to show you very quickly 3 stories that illustrate why this is powerful and why this is important. And they work not because we're so smart. They work because the system actually is using this electrical communication as a cognitive medium, as a decision-making substrate for determining growth and form of the organism. So the first thing I'm going to show you is a quick story about cancer. So if we take nasty human oncogenes like KRAS and P53 mutations and so on, and we inject them into tadpoles, they will eventually make a tumor. But before the tumor becomes apparent, you can already see, using this voltage imaging, you can already see that these cells have an aberrant voltage from their neighbors. And what happens is that voltage causes them to disconnect from the network. Once you've disconnected from the network, you can no longer remember this grandiose goal that you had before, where the collective was working on building and maintaining organs. As far as you're concerned, you're an amoeba. The rest of the body is external environment, and that border between self and world has shrunk. The cognitive light cone of that cell has drastically shrunk. It is not more selfish than other cells. It just has a smaller self. So cancer is in large part a dissociative identity disorder of the cellular collective intelligence, and it happens by breaking these electrical connections. Now that weird way of thinking about it has implications. It means that instead of trying to kill these cells, you can actually try to force them to reconnect with the with a pattern, with the other cells that are holding the memory pattern. And so we've done that here by co-injecting. So here you inject the oncogene, but you also inject an ion channel that's going to force the cell to be in the correct electrical state. And so these are the same animal, and so you can see the oncoprotein is blazingly strongly expressed. It's all over the place, but there's no tumor. Okay, and there's no tumor because it's not the genetics that drives, it's not the mutation that determines the outcome, it's the physiology and the cellular decision making. And these cells are remaining connected, and they are working on the same goal as they were before, making nice skin, nice muscle, whatever. Okay, so that's a story at the level of single cells. Now I'm going to show you what this means for birth defects. So here is here's a brain of a tadpole, and you can see here forebrain, midbrain, and hindbrain. And what we can do is we can introduce a mutant to a gene called Notch, and that's a very important neurogenesis gene. And so these animals have a very abnormal brain. The forebrain is missing. The midbrain and hindbrain are a big bubble. You can see the difference. These animals are profoundly affected. They have no behavior to speak of. What we were able to do is to build a computational model of the electrical pattern that normally tells the brain what size and shape it's supposed to be. And we simply asked the question, given this kind of disorder, what channels would you have to open and close to get back to the correct shape? And the computational model gave us an answer. And we found a couple of drugs already human approved. So this is already in use in patients for other reasons. But when you use them, here's what happens. The brain, now you got a normal brain. They have actually learning rates indistinguishable from controls, and yet they still have that mutation. Okay, so this is an example, and I'm not saying this will always be possible, but this is an example of fixing what is fundamentally a hardware error, meaning the mutation. You fix it in software. You fix it by a computer-designed, brief biochemical intervention that resets the electrical patterns so that the tissues know what to do, and then they make a correct brain. And the final story that I'm going to tell you is about regeneration, limb regeneration. So adult frogs do not regenerate their legs, unlike salamanders. So if they happen to lose a leg, then 45 days later, there's basically nothing. So we asked the question, could we communicate with these cells through the bioelectrical interface and guide them towards the leg growing path in anatomical space instead of the scarring path? And so we designed a cocktail, basically a 24-hour application of that cocktail ends up with driving about 1.5 years of leg growth. So at that point, immediately within the first 24 hours, you get the pro-regenerative genes coming on here. This is MSX1.
Getting all your daily nutrients is hard work, but nutrition gaps in your diet are inevitable.
You then, by 45 days, you've already got some toes, you've got a toenail, eventually a pretty respectable leg, and it's touch sensitive and it's motile. Okay, so again, keep in mind that in this case, we did not have to manipulate that process during that whole time. We didn't have to talk to the stem cells. There are no scaffolds here. We didn't have to micromanage it at all. We provided a very early signal that said, go down the leg building path. That's it. And so at this point, I have to do a disclosure because David Kaplan and I have a company called Morphoceuticals where we are trying to push this forward to biomedical use, is such that eventually, so now we're trying this in mammals, and so eventually you will have these wearable bioreactors, not just for the limbs, but potentially for all organs, that would provide the correct bioelectrical payload in terms of ion channel drugs. So that would then trigger the growth. Not trying to control every aspect of it because you have no idea how to do that, but to provide a trigger stimulus. And the final thing that I want to show you is the ability to induce novel organs, just to kind of nail the idea that what we're doing here is reprogramming the pattern memories of these cells. So I showed you that little eye spot in the electric face, and we wondered what would happen if we reproduced that same pattern somewhere else. So what you can do is inject into this early embryo RNA encoding a particular ion channel that produces a little pattern of particular voltage, and sure enough, those cells get the message and they build an eye. Okay, in this case, on the gut. These eyes have all the same layers, retina, lens, optic nerve, all the same stuff. And just notice what this means. First of all, it means that bioelectrics, of course, as I've shown you in these other examples, is instructive. It's instructive at the organ level. We did not have to say which genes to turn on. We didn't have to tell the stem cells what to do. We found a high-level subroutine call that says build an eye here. Okay, and the cells are very competent at doing that. The material, as I was pointing out, is not only competent to receive low information content stimuli and then have a very complex downstream response, but also it does this cool thing that other collective intelligences do. For example, ants. When ants come along a piece of food that's too big for them to move, what do they do? They recruit other members of the community. Well, these cells do the same thing. If we inject a few cells, they can tell there's not enough of them to build an eye. So what do? They recruit a bunch of cells from the environment that we did not inject at all. So there's the ability for the material to scale itself to the available to the message that they receive. And just to point out, if anybody's interested in plants, this is another great example of the plasticity of life. You might think that the oak genome encodes for this shape, because this is what you see most of the time. These acorns give rise to exactly this shape, this flat green thing. But along comes this non-human bioengineer, this wasp, which is a parasite, which puts down some signals for the plant cells, and it hacks them. It hacks the morphogenesis exactly the way that I've been showing you that we can hack the morphogenetic outcomes in animals, and it causes these plant cells to build this incredible spiky round thing, or even this stuff. So these are galls, and we would have had no idea what these cells are capable of if we didn't see this amazing example of bioprompting or reprogrammability. And in fact, it's kind of interesting that the sophistication of what is built is roughly parallels to the sophistication of the hacker. So bacteria and fungi make these kind of boring, lumpy things. Nematodes and mites do a little better, but by the time you get to insects, you get this beautiful kind of construct. So this is what we're trying to do. Is it took millions of years for the wasp to be able to do this. We want to accelerate this process. And so the last example I want to show you is a new kind of technology, which are basically synthetic biobots. So when you look at this, you might think that this is something we got from the bottom of a pond somewhere, but actually I could tell you that if you were to sequence it, it's 100% Homo sapiens. These are human adult tracheal epithelial cells. We have a process that allows them to reboot their multicellularity into this little creature. It's self-motile. Now, why is this interesting for biomedicine? What does this do? Well, and by the way, you would never guess that the human genome would make something like this. This is nothing like any stage of human development. Well, one thing they have the capability of doing is healing wounds. So if you make a bunch of human neurons in a culture like this, and you put a big scratch through the middle, right? So kind of a wound assay, and then you put these bots into their environment, they form this thing called a superbot cluster. And here you can see what they're starting to do. You lift them up 4 days later, you see that what they've done is knit the two sides of the wound together. So who would have thought that your tracheal epithelial cells that sit there quietly for a long time, just kind of getting rid of the mucus and so on, are capable of having a completely different life in a different form factor with the ability to heal some of your wounds. And This is just the beginning. This is just the first thing we discovered. They probably do a lot more. And so we're envisioning these anthrobots as personalized autonomous therapeutics. In other words, they're made of your own cells. If we inject them into your body, you don't need immune suppressing drugs. You're not going to reject them. They biodegrade within a few weeks. And in the meantime, there might be many applications in which these things could be cleaning out joints, looking for cancer cells, dropping off pro-regenerative molecules, fixing up neural connections, and so on. And so the bottom line is this. Much of much of biomedicine today is focused around these bottom-up technologies, so at the level of the hardware. But there's a whole frontier of medicine that's opening up, which are these top-down interventions that take advantage of the intelligence of the living material not to micromanage molecular states, but to convince the cells to and reset set points. We can train them. Here are the electroceuticals that I've been showing you, right, which are basically just signals to get the bioelectric pattern memories shifted in the right way. And of course, AI is going to be very important in enabling us to communicate to all the different layers of the body. So my claim here is that future medicine is going to look a lot more like a kind of somatic psychiatry and not like chemistry, because the name of the game is going to be to really take advantage of the intelligence of these other layers of the body. And the final thing I will just say is that because of the plasticity of life and because of the innate problem-solving capacities of tissues, pretty much any combination of evolved material, engineered material, and software is some kind of possible embodied mind. So in other words, cyborgs and hybrids and augmented humans and weird, kinds of creatures that you could only begin to imagine. Some of these already exist. Many are coming. They will be here with us in the future. And that means that we need to let go of old categories around living things versus machines and all that, because the entire variety of life, what Darwin called endless forms most beautiful, are a tiny corner in the space of possible beings. And I think we need to take very seriously the idea that this technology is not just about fixing all of the medical situations that plague us today, but also to release a kind of freedom of embodiment, where people really can reimagine their life in a very different way than the body they happen to have been given as an accident of the trial and error process of evolution. And we need to really work on a new way of synthbiosis of living up in a mutually beneficial way with beings that are going to be different from us. So I'll stop here. I'm just going to thank the postdocs and the students.
Okay, so there we go. That's his initial part. I'm going to stop the recording. Hold on.